Solving logarithmic equations. So if logs are present on both sides and logs have the same base, then we want to condense each side to a single log, then use one-to-one property of logs, which means if two output values are equal, then two input values should also be equal. If logs are present on one side only, condense using the properties of logs to get a single log on that side, then rewrite using the exponential form and solve it. Remember the domain restrictions of logs. Log of a negative number or log of 0 does not exist. Once we find a solution, we must check and make sure that that solution is not going to make any log of negative or log of 0 in the original equation. If that's the case, that will be extraneous solution. That would be not an allowed solution. If logs are present on both sides but have different bases, then we must use the change of base formula and convert both sides to the same base first. Let's see some examples. First problem, log to the base 2 of 2x minus 3 equals log to the base 2 of x plus 4. Good thing we do have logs present on both sides and logs have the same bases on both sides, so we can use 1-to-1 property, which says that if two output values are equal, then two input values should also be equal. 2x minus 3 should be equal to x plus 4. Let's go ahead and solve it for x. Subtract x from both sides and add a 3. X turns out to be 7. Now plug that x as 7 back in the original equation just to make sure that we won't end up with log of negative or log of 0, which is not happening. Both of them going to be log to the base 2 of a positive number. So we can box and say x equals 7 is our solution. Next problem, we have log on one side only. So I'm going to isolate that log and then write the corresponding exponential equation. 16 minus 4 is 12. Now go ahead and divide both sides with 3. So it comes out to be equal to 4. Now, when the base is missing, when we don't see a base for a log problem, the base is 10 in that case. So there's a hidden base 10 here. Now, once we have the single log on one side, we're going to write the corresponding exponential form, which is 10 to the 4th power equals 2x. So 2x is equal to 10,000 and x would be equal to 5,000. And that's not going to make, if I plug it back in, it's not going to give me log of 0 or log of a negative number. So it's okay, and this is going to be my solution. Next problem, again, the base is 10. We do have two separate logs on the left-hand side. We can use a product rule to write it as a single log with product of x plus 2, x minus 1 inside. So on the left-hand side, product rule gives me x squared minus x plus 2x, so that's x squared plus x minus 2 equal to 1. Once we have the single log, we are going to take help of exponential form. There's a hidden base 10. 10 to the 1st power equals x squared plus x minus 2 equals 10 to the 1st power, which is 10. That's a quadratic equation. Let's bring everything to one side and solve the quadratic equation. Two numbers that multiply to give me negative 12 add up to give me positive 1 are positive 4 and negative 3. When I factor them out, there's two solutions, x equals 3 and x equals negative 4. Now let's check both solutions. When x is equal to 3, would I get log of negative or log of 0 here? No, because when x is 3, I would have log of 5 plus log of 2 is equal to 1. So that's totally okay. When x equals negative 4, let's plug that in as well. Log negative 4 plus 2 is log of negative 2 plus log of negative 5, and that's going to be a problem. So negative 4 is not an allowed solution. X equals 3 is the only allowed solution. X equals negative 4 is causing domain issues because log of 0 or log of a negative number does not exist. We discussed it in the last video, why we cannot take log of 0 or log of a negative number. Next example, again the base 10 problem here. So we do have two separate logs with a subtraction in the middle. To condense them, I want to get them into a single log. I can go ahead and use quotient property. X squared minus 1 over x plus 1 equal to 3. Log of x plus 1, x minus 1 over x plus 1 equal to 3. We can cancel the x plus 1 and x plus 1. Log of x minus 1 equals 3. Now we can go ahead and use the exponential form, which is once we have the single log, we're going to take help of exponential form. X minus 1 is equal to 10 to the third power. X minus 1 is equal to 1000. X comes out to be 1001. And if I plug it back in to original equation, I will not have log of a negative number or log of 0. So always check your solutions. 5 natural log of 3 minus x equals 4. We want to get the log term alone. So natural log of 3 minus x equals 4/5. Now, we're going to go ahead and write the corresponding exponential form. Natural log has the base e. So e to the power 4 over 5, e to the power 4/5 equals 3 minus x. I'm going to try to solve for x. X comes out to be 3 minus e to the power 4/5, and that's my exact solution. X here, we brought the x to this side, and 3 minus, so that's going to be 3 minus e to the power 4/5. All right, now we want to check and make sure that that does not leave me with log of a negative number or log of 0. I'm going to leave that part for you. So go ahead and check, plug it back in, 3 minus e to the power 4/5. Make sure we don't get log of 0 or log of a negative number. Next problem, we have log to the base 2 here with a plus sign in the middle. That means I'm going to be able to use the product rule, and I can express it as a quotient. I can express it as a product of log with a single log with a product equal to 2. All right, log to the base 2, that would be x squared minus x plus 2x, which is plus x minus 2 equal to 2. Now, x squared plus x minus 2 is 2 to the second power. X squared plus x minus 2 equals 4. Let's bring everything to one side and solve this equation. And again, looks like I'm going to have two solutions here. X plus 3 and x minus 1 are the factors. So my two solutions are 1 and negative 3. If I plug x as 1, that's okay. But if I plug x as negative 3, it's going to leave me with log of a negative number, and that's going to be a trouble, and that's not allowed. So we'll have to exclude the solution as negative 3. X equals 1 is the only solution. Now, sometimes negative solutions are going to be okay and allowed, so always plug it back in and check. Don't just assume that negative solutions are going to be an issue. Next problem, we don't have log of a quotient, but we have quotient of two logs. So how do we handle this quotient of two logs? Let's see. We can go ahead and take log x to the other side. Now both sides have the log to the base 10, but on the right hand side I don't have the log term by itself like I have on the left hand side. So my goal is to get the log term by itself. Turns out to be log of x squared. Now we can use one-to-one property, which says that if two output values are equal, then two input values are also equal. Let's bring everything to one side and factor and solve. X squared minus 3x plus 4 equal to 0. Now, let's see if it's not factorable, so I'm going to quickly think about b squared minus 4ac, which is negative 3 squared minus 4 times 1, 9 minus 16, a negative number. So there's no real solution for this problem. Even if I use quadratic formula, I'm going to have imaginary solutions with i's. There's no real solution for this problem, and we'll just stop at no solution. Next problem, again, left hand side, right hand side, I can use a property of logs, which is I have difference of two logs, so I can write them as a quotient. But on the left hand side, I don't have the log by itself, but I can use it, use that 2 as an exponent and have a single log on the left hand side. Now we can use one-to-one property because we got a single log on each side. Y plus 2 squared equals y plus 2 over 12. Let's go ahead and solve it. 1, we can make our life easy by cancel one of these factors here. So we'd be left with y plus 2 equals 1 over 12, which gives me y is equal to 1 over 12 minus 2, which is negative 23 over 12. And if I plug that back into the problem, negative 23 over 12 is going to be less than negative 2. So, and if it's less than negative 2, we would not have any issues with log of a negative number or log of 0. So this is going to be an allowed solution, because if I plug it back in, I will not end up with log of 0 or log of a negative number. If I had negative 2 or something bigger than negative 2, that would be an issue, because then I would end up with log of a negative 0 or log of 0. Log of 0 or log of a negative number. But that's not happening here. Next problem, natural log of x equals log to the base 10 of x. Now here's a little issue because we don't have the same base on both sides. So first thing we want to do is we want to write both sides with the same bases and then go ahead and solve it. So what we can do is we can write the right hand side natural log of x as natural log of x as over natural log of 10. Okay. Which gives me natural log of 10 equals natural log of x divided by natural log of x, just rearranging the terms, and that turns out to be 1. Natural log of 10 is equal to 1, which if I write the corresponding exponential form, it means e to the first power is equal to 10, which is not true. That means, again, there's no solution for this problem. There's no values of x that can make this equation true. That was all for this video. We saw 9 examples of solving logarithmic equations.